Good afternoon. Today we're going to pick up where we left off last time. We're in Chapter 4 and we are discussing the diode as a device. This provides a nice follow-up to Chapter 3 where we talked about semiconductor physics, or an overview of semiconductor physics, and then used the p-n junction or the structure of the p-n junction as a way to demonstrate how semiconductors work. So now we're in Chapter 4. We're no longer talking about the physics or the chemistry behind the way that a p-n junction works. We're more focused on the way that a diode operates or behaves within a circuit. So it's VI characteristic, and how can we solve circuits that have diodes inside of them. Last time we talked about a half-wave rectifier, we talked about designing a logic gate that used diodes, and we also talked about, anyway, some various applications. But now we're getting more into modeling, and what we saw was that there's four main models we're going to use to describe the diode. We've already talked about the ideal diode model. The exponential model is the one that we derived in Chapter 3, but two we haven't touched upon yet, the constant voltage drop model and the small signal or linearized model. So the exponential model is shown here. We're very familiar with this equation. It's the most accurate representation of the diode that we have, or that we use in this text at least. However, it's going to be the most difficult to employ in circuit analysis. This is a nonlinear model. All the methods that we have learned previously, especially those in ELC251-11, are linear in nature, right? They rely on linear algebra, and so any circuit or any system that has this nonlinear representation, nonlinear model within it, we cannot apply the nodal and mesh analysis to it. So how can we solve a circuit like this one right here with a diode in it if we represent it using the exponential model? So we're going to start off with this example. We're given a DC voltage source of 5 volts, a 1 kilo ohm resistor, and then a diode, which is defined by its rated value. So it conducts 1 milliamp of current at 0.7 volts across the diode. You'll see that diodes are often described in this way within the textbook, which probably for you and I, at least at this early point in the chapter, it makes the most sense to be given the IS value, that constant. However, the textbook gives it to you in terms of these rated values, and you can work backwards to determine what the IS value is for it, the I saturation value. Now, there's two methods that we're going to use to solve this circuit. There's the graphical method and there's the iterative method. We're going to go through both one by one. And what we're going to see is that they have individual strengths and weaknesses, although the second, the iterative method, because of its efficiency when implemented as an algorithm on a computer digitally, the strength and the efficiency that it has there makes it, at least today, probably the more practical, the stronger method. But anyway, let's talk about using graphical analysis to solve this circuit. So you'll see here that, as you would expect, the graphical analysis is based on drawing something, drawing a figure, drawing a graph. And there's two lines here. Why are there two lines? So if we go back to the previous slide, what we'll see is that there's really two constraints that we have to worry about for this circuit, two constraints that we have to satisfy. The first is KVL, right? This current had better be equal to VDD minus VD over R. We cannot violate KVL. The other constraint we have is that ID had better be equal to IS equals e to the VD over VT. We need to satisfy both of those, and so we draw two lines, one representing each of those constraints. Here we see the exponential model for the diode, and here we see what's called the load line, which describes KVL and the current in terms of the series resistance. And so the graphical method, after we graph both the constraints, graph both the lines, is essentially just finding the intersection between the two of them. And that intersection we're calling Q. That's the operating point, and that's essentially the solution to the problem. Now, how do we find the intersection? If you're doing it using a graphing calculator or a computer, then you would have some sort of a function that you would call. If you're doing this by hand, then there's a little bit of approximation that would be involved. It's an interesting method. As you can see, it's rather intuitive, but in today's world where we have access to so many digital tools, it's probably not the one that you're going to default to. So the pros of the graphical analysis method, the main advantage is that it is intuitive. Again, you can see what's going on and really understand what it is that you're trying to do, which is to satisfy both constraints. There's many cons. The precision, if you're doing it by hand, is going to be relatively poor. Now, if you're doing it digitally, that's a whole different situation. And it's not really practical for complex analyses because multiple lines will be required. So the more components you add to the system, the more branches, the more diodes, the more that you add, the more lines you'll have to draw and different types of intersections that you'll have to find. And so quickly you can see that the graphical method becomes less and less practical as the circuit gets larger and larger. This is just homework 8, which has already been assigned to you. Okay, so now, jumping back into lecture. We talked about the graphical method. The other method, the second of the two, is iterative analysis. And so the iterative analysis method is one that you can do it by hand, but it's probably better implemented as an algorithm that you run digitally. And these are the basic steps in that algorithm. So we start with an initial guess of what the voltage across the diode is. A lot of times we'll use a value of 0.7 volts. Then what we'll do is use nodal mesh analysis in order to solve for ID. We could also use simply KVL and KCL combined. In other terms, what we have to do is we have to solve for ID from the value of VD that we assume. Then what we use is the exponential diode model to update VD. So what we'll do is we'll take this value of ID that we solved for, we'll stick it into our exponential model, get a new value of VD, and then essentially step 4 is telling us to return to step 2. So we take this updated value of VD, we calculate ID again, stick the ID in here, calculate the updated value over and over until we reach convergence. So upon convergence, the new and old values of VD will match, meaning that if, let's say we're at iteration 15 and we get a value of VD 0.75, iteration 16, again 0.75, then we can be confident that, that we have at least one solution to the circuit we've converged. And so there's an example in MATLAB that I'm going to post online. I'll send out an email about that. All right, so the advantages of the iterative method: precision is relatively high, especially if you set the convergence criterion properly. Right, so we can determine how precise the iterative algorithm will be. If we look for a very close match between two consecutive values, we'll get a very precise answer, but that will most probably require a lot more iterations. For relatively small systems, that's not problematic, but as we get to larger and more complicated systems, that potentially will be a limiting factor. Now, disadvantages or cons, it's not as intuitive, right? It's heavily mathematical, so I don't necessarily know if it gives the same big picture explanation or view of what's going on. And I mean, I know it's sort of hypocritical to say that both are not practical for complex analyses. Perhaps I could reword this. It's not that the iterative analysis isn't practical for complex analyses. It's really that it's not practical to do it by hand for complex analyses. Okay, as the number of iterations grows, it makes more and more sense, like I've said several times, to implement this digitally. But I think a digital implementation is practical. And in fact, right, many simulation software packages like your PSpice use methods that are somewhat similar to iterative analysis. All right, so next question is, how can one analyze these diode-based circuits more efficiently? We just saw that using the exponential model has its disadvantages. And so how can we do this more efficiently? We need to find a simpler model. Now, one simpler model we've already talked about. That's the ideal diode model. But perhaps that's a little bit too simple. Is there something in between that we can rely on? So one simpler model is called the constant voltage drop model. And what we're going to do is we're going to take the exponential model, which is reflected by the blue line, and we're simply going to break it into a piecewise function, where, again, it blocks for anything below this value here, and then it conducts at this specified value, which in this graph is 0.7 volts. It's very similar to the ideal diode model, almost as if it's just simply shifted to the right. So the constant voltage drop model assumes that the slope of ID versus VD is vertical, straight up at 0.7 volts. So what we do is we take the curvature here and we approximate that by a straight line. Now, how does the solution to example 4.4 change if the constant voltage drop model is used? When we use iterative analysis, and you'll see that when I send the MATLAB code for this example, the solution that we got was 4.262 milliamps. That was from the iterative method, which should give us a very accurate result. Using the constant voltage drop model, that only changes to 4.3 milliamps. So you can see it's a relatively small difference in the solution. And as we'll see when we go through an example of using the constant voltage drop model, it's a lot easier to solve, because now we do have a linear circuit element, one that we can represent and incorporate into analyses like nodal and mesh analysis, things that we're used to from ELC251-11. Now, the ideal diode model we've already talked about at length. We spent a good chunk of last class talking about the ideal diode model, so I'm not going to rehash that. The main thing I'm going to focus on is how does the solution from example 4.4 change if we use the ideal model. So we saw it went from 4.262 to 4.3 milliamps when we went from exponential to constant voltage drop model. And when we go from exponential to ideal, the change is pretty stark. Right? We go from 4.262 to 5 milliamps. That's a much bigger jump. So you can see that the constant voltage drop model is a really nice medium between the exponential and the ideal diode model. It's linear. It's almost as easy to use as the ideal diode model, really. And it provides us a significantly more accurate representation of the way that the diode behaves. So when do we use these models? And I think that's one thing that we take away from this chapter. There is no good or bad model, although I'm sure there are models that are objectively bad. But in terms of what we're talking about here, each model is appropriate for a different type of application. So let's say, for example, the exponential model. The exponential model is going to be important to use when we have a real emphasis on accuracy over practicality. It's going to be good to use in less complex circuits. And it's going to be more important to use at low voltages, because really at lower voltages, that's where we see the biggest difference between the way that the exponential model behaves and the ideal or the constant voltage drop model behaves. Now let's go to the other end, the ideal diode model. So the ideal diode model is going to be most advantageous to use when the voltages are much higher than 0.7. So that curvature in the exponential model really, from this blown out view or from this wide view, will look like the ideal diode model. So for higher voltages, very complex circuits that have tons of diodes, where we simply just cannot afford, let's say in a computational sense, to use more complicated model, and cases where the difference in voltage by 0.7 volts is negligible. So if we're dealing with a circuit, let's say a power electronic converter that has hundreds of volts running through it, a solution or a difference in the solution by 0.5, 0.7 volts is probably not going to have much effect on the design or the way that it operates. And that would be an application where the use of the ideal diode model would be good. Now, constant voltage drop model is, again, sort of in between. It's good for cases where we have an emphasis on, let's say, practicality and accuracy. Both for more complex circuits, again, sort of in between the two, and medium voltages. If we have really high voltages, again, going back to the power electronic example, there's no point in using the constant voltage drop model because that value of 0.7 is going to be negligible anyway. But I would say, right, these two have similar applications, and this one is a lot different in terms of the way that it's used. So the last model here, which we haven't talked about yet, is the small signal or the linearized model, and that's what we're going to talk about next. So the small signal diode model, what is it? In the small signal diode model, the diode is modeled as a variable resistor whose value is defined as a linearization of the exponential model, right? So we take the exponential model, which is curved, we pick an operating point, we find the slope at that point, and that slope will represent a linear relationship between voltage and current. What do we call a linear relationship between voltage and current? Right, we can call that resistance or conductance. And so around a bias point, that is where we're going to perform our linearization. In most cases, we're going to use the assumption that the linearization point or the operating point is Vd equals 0.7 volts. So how is the small signal diode model defined? There's a little bit of a process here. So what we're going to have to do is we're going to have to take the circuit and we're going to split it up into two different parts. We're going to split it up into what we call the static or the steady state component and then the time varying, sometimes we'll call it the AC component, although that's not the best name for it. So the total instantaneous circuit, total instantaneous just means everything. So what you would see if you were looking at the input or output on an oscilloscope is divided into, like I just said, the static or steady state and time varying components, which may be analyzed separately and solved via algebra. Now, why can we do this? Because we are linearizing the model. When we linearize the model, we can then apply superposition, and superposition tells us that we can separate the inputs, look at their effects separately, calculate those effects or those outputs, and then impose them on one another or add them back together depending on well, in this case, it's going to be addition. So how are we going to represent the diode for the two different circuits? So for the steady state or static circuit, the diode will be represented as a constant voltage drop using the constant voltage drop model, the one we just talked about a couple minutes ago. And the time varying circuit, the diode will be represented as a resistor, which again we'll talk about in a moment how to solve that. Now, neither of these circuits employ the exponential model, which makes the process easier, the solution process easier, because now we had one circuit where we needed to solve for an exponential model. Now we have two circuits which may seem more difficult or more time that would require more time, but now neither of these circuits use the exponential model, which is a huge plus. So this figure here, figure 414, does a great job of sort of describing how we split up this circuit. So we start off with a circuit that looks like this. And the one thing I should say before we go too far into this, the small signal model is not going to apply to all different types of problems. It's going to be rather focused and specific in the way that we use it. And so when you start to see some more examples of implementation of the small signal model, it'll make more sense why things are shown in this way. So let's assume for a second that we have a signal that has a DC and an AC component. We could also call it the steady state / static component and the time varying component. It's connected to a resistor in series with a diode. So what we're going to do is we're going to split this up into two different pieces. One piece will be the static, the DC, the steady state component, whatever we want to call it, in series with a resistor and a diode. But we're going to represent this diode using the constant voltage drop model, which means that when it's conducting, it'll be represented by an 0.7 volt source. When it's blocking, it'll be an open circuit. Then we take the time varying or the AC component and we put that in series with this same resistor. All three of these big R values are the same, as well as a new resistor. So we're replacing the diode with a new resistor that we're going to call little r, little d. So what you see is that the total instantaneous solution is equal to the static solution or the steady state solution plus the time varying solution. It's important to note the way that variables and subscripts are used here. The total instantaneous solution or any total instantaneous value will always be described by lowercase variable uppercase subscript. The time varying component of any value will be described by lowercase variable lowercase subscript. And then the steady state or the static solution or component of any signal will be uppercase uppercase. So what we have is lower upper, upper upper, lower lower. And as we get more into these types of problems, what you'll see is we'll begin to rely more on the notation and less on being so explicit. Okay, so let's go through an example and try to apply the small signal model. So question, how is the small signal diode model defined? Let's consider the circuit shown here. And in reality, right, these two signals are not two separate signals. This may be a DC signal with noise, or it may be an AC signal with a significant DC offset, right? What you want to do is think about this as a single signal that we're trying to decompose into the time varying and static components for the purposes of this problem. So the static voltage is big V, big D. The time varying component of voltage is little v, little d. And both of those are applied across this diode here. This slide simply just repeats what I said a second ago about the notation. Again, static is uppercase with uppercase subscript. Time varying is lowercase with lowercase subscript. And total instantaneous is lowercase with an uppercase subscript. This equals this plus this. And one more time I'll repeat, right? Static component, in certain cases we also call it the steady state component. And then I try to shy away from this term. We also called it previously the DC component. The time varying component was one that we also, again, I don't like to use that reference, but we called it the AC component. Okay, so we start off by defining the static current in 4.8. So what we know is that for the circuit, now actually let me start off by asking a question. We know we have to split this up into two different sub-circuits. So what is the static / steady state circuit going to look like? We'll have this voltage source here. This will not appear in the steady state or static circuit. And we'll have this diode, which will be represented by the constant voltage drop model. Okay, so for the static circuit, we can use the exponential model to represent big I, big D equals the saturation current times e to the big V, big D divided by VT. All right. Next step, equation 4.9, what we want to do is we want to define the total instantaneous voltage, which is little v, big D, as the sum of the static and the time varying components. Again, this is still following the appropriate notation, lowercase, uppercase, 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 lowercase, lowercase. Next, we want to define the total instantaneous current as a function of the total instantaneous voltage. This is just a restatement of the exponential model that we've seen before. ID equals IS, e to the VD over VT. These are both the total instantaneous values. So one thing that we can see is that this can be plugged in to, so equation 4.9 can be plugged into equation 4.10. Now, that's what we did in step number 5. If you look, I took this and plugged it in right here, which gives us this form of the equation in 4.11. We know that if we have e to the alpha plus beta, that can be split into e to the alpha times e to the beta. So we can take this term right here, and we can split that up into two multiplied terms. And so the last step that we can take here, and I want to talk about this equation for a second. So we've gone through a couple steps. What we end up with is that the total instantaneous current is equal to the saturation current value times e to the Vd over Vt using the static value times e to the Vd over Vt using the time varying value. If you remember, look at what's inside this box right here. That is the same thing that we defined in the very beginning. Because this step seemed a little bit out of place. Why did we say this first? And so what we end up with, 411 and 412 really are just the exact same equation, but with this piece collapsed. So the total instantaneous current is equal to the static current, big I, big D, times e to the little v, little d over Vt. Now, I think at this point it's important to understand the derivation, to take in what we're talking about, but like many topics in this chapter, it becomes best or most evident how to apply it once you start getting into the homeworks and the examples, which we're going to do an example right now. Okay, so does this really help us, equation 4.12? Is it easier to solve? No, it's still exponential in nature. So if we were to take this and use that representation to solve this circuit here, we'd still have to use graphical analysis or iterative analysis. So that's not really providing us any advantage. So what can we do to change that? What we're going to do is we're going to apply a power series expansion to this equation 412 right here. And so what that power series expansion says is that e to the x, and this is just one example of a power series expansion, e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, so on and so on and so on. And so what we can do, right, we can replace e to the little vd over vt with Vd over Vt plus that value squared over 2 factorial plus that value cubed over 3 factorial. And so that's what we have here, where we're using little v, little d in place over Vt in the place of x. So what we did was we took this value, and we replaced it with the power series expansion of it. Now, again, this is not very helpful, right? This is probably what seems to be, this equation is getting more and more complex with every step. However, now what we can do is negate the higher order terms, which we assume will have less of an effect on the answer, assuming that Vd is very small. Right? This is similar to the concept of linearization, that for small values of our signal, as long as we stay relatively, again, we keep that small, the first two terms will give almost as good of a representation or almost as good of an answer as the full expansion. As Vd gets larger and larger, we will need more and more terms to represent it. And that's the reason why this is called the small signal model, because right here, going from 412A to 414, where we eliminate the higher order terms, this jump only makes sense if we are using, or if Vd, little v, little d, is very small. This jump does not make sense if that value of little v, little d is larger. So now, the small signal approximation. It's shown to the right. What we see is that the total instantaneous current is equal to the static value of the current plus the time varying component. We're also going to call this the small signal component. Now, the small signal component of ID is equal to 1 over RD times VD. Now, where do we get that from? If you look at this initial equation here, which comes from down here, what you'll see is, right, ID, big ID, static component. Small signal component is equal to the large signal component divided by the thermal voltage times VD, small v, small d. Now this, given what we see right here, can also be represented as VD over RD, where we are, I don't want to say making up, but we're introducing this new value, which we're calling the small signal resistance. So if we compare this equation to this one up here, what value of RD makes these two equivalent? And the answer is VT over big I, big D, right? Because if we take this right here and we insert this, we end up with little I, little d is equal to big I, big D over VT times little v, little d, which is the same thing that we have right here. So this value comes from a comparison of this form that we want and this form that we got from the previous slide. So again, we have our static current, we have our total instantaneous current, and then we have our time varying or our small signal current. The small signal current, now we figured out a way to represent that in terms of a small signal resistance, which is defined by VT, this is a constant, and ID. Now how are we going to come up with big I, big D, the static value of ID? We are going to come up with that by solving the quote-unquote other circuit. Remember, we split it up into two pieces. We first have to solve the static circuit, and then we'll solve the time varying. Now, this approximation is good for values of small v, small d, less than 5 millivolts in amplitude. This is not peak to peak. This is just amplitude. So when we use the small signal model, what we have to do at the very end is check to see whether the variation or the amplitude of change in little v, little d is greater than 5 millivolts. If it is, then we may want to use a different model. And I would say for the purposes of this class, we're going to say that means that we can't use this model. That's not an appropriate use. The signal is not small enough. Now, so how is the small signal resistance defined? I think we already said this, right? RD is equal to the thermal voltage divided by big I, big D, which is the static value of the current. A little bit of repetition here. Okay, now example 4.5, I think this is going to be the real aha moment. This is the best way to understand this model. The derivation, the initial model presentation is perhaps a little bit difficult to understand intuitively. It's not easy for me to explain, to be honest, but the example makes it crystal clear. So let's consider a circuit that's shown in 414A, okay, which is here. And it has a series resistance of 10 kilo ohms. Now, the power supply, which is called V plus up here, okay, it has a DC value of 10 volts, which is the static or steady state value, over which is superimposed a 60 hertz sinusoid of 1 volt peak amplitude. This is known as the supply ripple. So one way that we can think about this problem is we have a DC source and it has some noise or ripple component in it that's coming from another, that's caused by something else, external to this problem. And so now what we want to do is we want to figure out what is the result in VD of applying our input that's essentially 10 plus the 1 volt ripple. We can't do that using the ideal model or the constant voltage drop model reliably. We can do that using the exponential model, but we know that's going to create a lot of difficulties in terms of calculation. So the small signal model gives us another compromise, where as long as small v, small d stays below 5 millivolts amplitude, it should give us a very accurate answer. All right. And so again, we're going to assume the diode to have an 0.7 volt drop at 1 milliamp conducted through it, and this is how they define the behavior of the diode itself. All right. So let's consider the circuits to the right, and let's split this up into its different pieces. So we have initially a resistor in series with a diode. This is going to be a 10 volt source, and this is going to be a 1 volt sinusoid. We split it up into B and C. This is 10 volts, the same resistance as we see over here, and this is going to be represented by a constant voltage drop model. Okay, essentially an 0.7 volt source. Our time varying or our small signal circuit will have the 1 volt sinusoid in series with the resistance. This resistance is the same as this, is the same as this, with our value of with our small signal resistance. This is equal to, if you remember, it's a function of big I, big D, as well as the thermal voltage. So this is what the split looks like. And now let's jump into the math a little bit. All right, so we want to define the model to be employed. This is, we don't really necessarily need to do this. This is a little bit of repetition from how we derived it. But jumping into step 3, and let me take a step back here. The basic approach to this problem, or the process, is going to be you have your total instantaneous circuit, you split it up into your static and your time varying components. You solve the static / steady state component first. You get your value of big I, big D. You take that, you plug it into your small signal model because you need that in order to calculate the small signal resistance. And then you solve that one, and then you have your full answer. So, like I said, we start off by solving the steady state / static circuit. And for that one, all we have to do is use KVL. So if you look back at this circuit here, this is going to be 10 minus 0.7 over R will give us the value of current flowing through this circuit, which is big I, big D, static value. All right, so we have 10 minus 0.7 over 10,000. Big I, big D is 0.93 milliamps. Okay, now, next step is we need to set up our small signal circuit. So we know that the small signal resistance will be equal to 25.8 millivolts divided by 0.93 milliamps, which gives us 26.9 ohms. Okay, now we want to solve our small signal circuit, which is going to be relatively easy. Again, we know that this is 10 kiloohms. We know that this is 26.9 ohms. And so this looks like a voltage divider, which means we can solve using this equation here. Our ripple has a 1 volt amplitude peak. We plug in our values, 26.9 ohms, 10,000, 26.9 ohms, and the result is we get a 2.68 millivolt peak amplitude of the output across the diode. So if we go back and take a look at this right here, what the answer is telling us is that if this is 10 volts DC and this is 1 volt time varying, what is going to be the output that we observe here? It's not going to be a 1 volt ripple in the voltage across the diode. It's going to be much smaller. It's going to be only 2.68 millivolts. So one thing that we'll see as we move into the next section is that the diode has the ability to regulate voltage in order to reduce or remove ripples from a signal. And that can be very advantageous for a lot of different applications. So, like I said, the diode can help us regulate voltages. One way of using that is something called a voltage regulator. So what is a voltage regulator? It's a circuit whose voltage output remains stable in spite of changes in supply and load. The previous example was an interesting pseudo-example of a voltage regulator, right? Because the input ripple was large, it was 1 volt, and the output ripple was much smaller, it was less than 3 millivolts. So what characteristics of a diode facilitate voltage regulation? And that has to do, well, one way of describing it is the approximately constant voltage drop across it, as well as what we saw earlier in the chapter, where huge changes in the current result from very small changes in the voltage across it. I think it was something like, what was it, a 10-time change in the current was associated with only a 60 millivolt change in the voltage across the diode. Okay, so let's take a look at this example, 4.6, and let's solve. This is an example of a voltage regulator, and we're going to be using the small signal model again to solve this. So consider this circuit shown here in 415. It has a string of 3 diodes used to provide a constant voltage of 2.1 volts. So if we look at the desired value, each one of these diodes provides regulation with a nominal value of approximately 0.7 volts. So if we have 3 in series, that will give us 2.1 volts. Question asks us, first part, what is the change in this regulated voltage in the output caused by a 10% change in the supply voltage? All right, let's see what that result is. So we have, again, what can be broken down into a static voltage, 10 volts DC, and a time-varying voltage, sine with an amplitude of 1 volt. We have this series resistance, and we have these 3 diodes in series. We're not worried about the load resistance just yet. So we're going to follow the same process that we did last time. We need to take the total instantaneous representation, split it up into the static / steady state representation as well as the small signal / time varying representation. We need to solve the steady state / static circuit first in order to come up with the value of big I, big D. We're going to take that, plug it into our equation for the small signal resistance, little r, little d, in order to come up with that value. We take that, place it into our small signal circuit, and then we solve our small signal circuit, which will give us the amplitude of the ripple in the output. Okay, so let's solve the static circuit first. So if we go back here, what do we have? We'll have a 10 volt source. We're not using the 1 yet. So it'll be 10. These are all going to be represented by constant voltage drop models. So that'll be 0.7, 0.7, 0.7, 3 in series. So 10 minus 2.1 over 1 kilo ohm. So 10 minus 2.1 over 1 kilo ohm gives us 7.9 milliamps. I know I forgot the kilo here, but it's taken into account when we get the solution. Next, we take this and we plug it in here to get our value of the small signal resistance. So small signal resistance is 25, or unfortunately in this book they use different values for VT every time. But so here we're using 25 millivolts divided by 7.9 milliamps, and that gives us a value of 3.2 ohms. Now, since we have 3 of them in series, we have to represent the diodes as 3 small signal resistances. So we'll have 3.2 ohms, 3.2 ohms, 3.2 ohms. All right, how do we solve for the output? So if I go back to the circuit here, what you'll see is that now if we look at this from the point of view of the small signal, what we'll have is a 1 volt amplitude sine wave in series with a 1 kilo ohm resistor in series with 3 3.2 ohm resistors. So if we want to figure out what V out is, we have to look at this as a voltage divider, 9.6 ohms and 1,000 ohms. And so that's what we do. 9.6 ohms over 9.6 ohms plus 1,000 ohms. We multiply that by the peak of the input, which here we're instead of using amplitude, we're using peak to peak, so we're going to multiply it by 2. So 2 times 1 volt times the voltage divider gives us a peak to peak ripple in the output. A peak to peak ripple seen right here of 19 millivolts. So the question that I ask after that is, and we kind of forgot to do this with the previous example, we need to check whether we're satisfying our condition for using the small signal model, which is essentially that the amplitude of the voltage across the ripple across the diode has to be less than 5 millivolts. So is that satisfied here? The answer, although it may seem like no, is actually yes. And there's a little bit of a conversion that we have to use. So first off, the 5 millivolts is not compared to the peak to peak value, it's compared to the amplitude. So we need to start off by dividing this by 2. So that brings us down from 19 to 9.5. That's still above the 5 millivolt limit. So there's another little bit of a conversion that we need to do where essentially now, so that 5 millivolt limit was for a single diode. So we have 3 diodes in series, which means that that ripple is going to be divided evenly between the 3 diodes, and therefore the ripple across each diode is not 9.5, it's actually 9.5 divided by 3. So anyway, you can see here from the math, right, we have a 19 millivolt peak-to-peak ripple. We divide by 2 to go back to amplitude from peak to peak, and it should be divided by 3 diodes. So there's really only a 3.2 millivolt amplitude ripple across each one of the diodes, which does stay within the 5 millivolt limit that we set before. Okay, operation in the reverse breakdown region. Under certain circumstances, diodes may be intentionally used in the reverse breakdown region. These are referred to as Zener diodes. They talk about this more in the textbook. For better or for worse, this is not a topic we're going to really heavily dive into now. We're going to try to come back to it a little bit later.